All right, well, welcome back to class number 12. And here is another example from Cengel. I want to find the enthalpy of a compressed liquid, and we're going to use a couple different methods. First, we can find it by looking it up, right? So it just so happens that we're lucky enough when we're at 15 megapascals and 100 degrees Celsius that we can find in the compressed liquid tables the value for this. That's not always possible. It's not a extremely well incremented table, but this particular one happens to be in there. So that's table B14 right here. And so you see a 500 kPa, 2000 kPa, but we're looking for 15,000 kPa right here. So that's 15 megapascals, and we're looking for 100 degrees. So here you go for we're looking for enthalpy. Yes, we're looking for enthalpy right there. So we have 430.26 is the exact right answer. So let's write that down. So that's for part A using the compressed liquid tables. And so that's table B.1.4 at P equals 15,000 kPa and T equals 100 degrees Celsius. We found that H was equal to exactly 430.26 kilojoules per kilogram. Now let's try it here by approximating it using the saturated liquid, or treating it like a saturated liquid. All right, so what we're going to do is we're going to go to, we have a choice either to go to 100 degrees Celsius or 1500 megapascals. I'm going to think that we're going to be better off going to here. I don't think we have that in table. Well, let's just take a look. Let's just take a look at both. Table B.1.1 at T equals 100 degrees Celsius. Let's see what we can learn from that. All right, so here we are, table B.1, and we come down here, and oh, okay, so this internal energy on this side. Never mind my knuckle. That was gross. There's 100 degrees Fahrenheit. No, excuse me, Celsius. And what we want to have is the fluid enthalpy right here. So we get 419.02. So let's write that down. H is 419. That's interesting. That's HF, by the way. 419. My short attention span just forgot what it was. Short attention span wins 419.02. It's interesting that this is actually different than was in the example in Cengel. They have 417.44, so their tables are different, ever so slightly different. It's interesting. So we should get what the percent difference is here. Okay, so this is an estimating thing. So this is the correct one, and this is what we're using for estimation. So here, I'm going to go the absolute value, and we go this one divided by the correct one. So 419.02, 430.26, and 419.02, 430.26 divided, subtract 1, and we have that's 2.612% difference less, right? So this is 2.612 less than that, so we would have an error of that. But now let's try it with, they're saying using using the correction given by equation 438, and that's this guy. So what they're saying is to take this that we just found right here and add to it the specific fluid volume times P, the pressure, that's 15,000, minus the saturation pressure. So we should, while we're still here in table B, 0.1.1, for that value, we can look up the saturation pressure. Am I doing this incorrectly? I feel like I'm doing this incorrectly. Because I'm getting a different value. I guess the other book was, they had 99 point, oh, that's interesting. Maybe it's the newer edition has the 99. Anyway, we'll go 101.3. We'll use that. And then we'll also use the fluid specific volume of 0.001044. Yeah, I think it's because the 10th edition has a slightly different table. They might have updated it. So updating my table B 0.1.1 at T equals 100 degrees Celsius. PSAT, according to this, is 101.3. Boy, it really feels like I did something wrong. Maybe. I might have been tired yesterday. It's probably I did something tired yesterday. So VF at that is going to be, so maybe I'll fix it on 0.001044. And these are cubic meters per kilogram. So we could say that our H estimation is going to be HF at T plus VF at T, and P minus P sat at T from what we have. That's right up above. I guess I didn't have to write it, did I? H is going to be 419.02 plus 0.001044 times 15,000 minus 101.3. And let's see what we get. We get 419.02, and I'll go this one first. 15,000, 1.3 minus, and then 0.001044 times, and then plus, and we get 434.57. And then we can find out what the percent difference is. We'll take 434.57 and divide it by the known 430.26. So 430.26 divided 1 minus, and we get 1%. 1.003%. Larger or more, whatever you want to say, larger. Something I wanted to check on this while doing it. I wanted to see, I meant to, I was referred to it. Let's go to table 1B.1.2 and see if it goes all the way up to 15,000. It does. So here's B.1.2. It goes to 15,000. So let's take a look at the fluid. Ooh, wow, that's completely erroneous. Fifth right here. All right, so that's no good. That wasn't going to be helpful to us at all. So it was really sort of, you could say that, well, it's closer to the temperature one, the pressure one. It's going to be much higher. It's a higher temperature, So the saturation temperature is much higher than what would we say 342. Yeah, so that kind of makes sense. It's more of a temperature dependent thing. You'll recall that we find an estimation of enthalpy can be found from a change in enthalpy can be found by CP, CP, I think, delta T. I don't think you can find the enthalpy by simply multiplying this. And of course, it's for steam, so that's, or for water, I should say, by this temperature. We could try that out, though. Let's try it out. Let's see what happens. Maybe it'll work out. So we can go to, so here's my what if type of thing. What ifs are good. I hope to organize your brain, keep you thinking, make you think. So let me see. This would be in table A, 0.5. We have steam, right? But we don't have steam right here, so we can't really use this. That's for steam. We need to use it for water. So let's see. We need liquids, and water is a liquid. Here you go. We have a CP of 4.18. That's going to be pretty easy math, right? Because we're going to multiply that by 100 degrees, so we're going to get 418. Interesting. We're close to it. We're actually close. So this is 4.18. And that's, let me see, let me cross that out. Let's see. We don't know if this is true. Let's just go CP times T, right? So then 4.18 times 100, we get 418 kilojoules per kilogram. And it's not terrible. I don't know, 430, so the percent difference is going to be 1 minus 418 over 430.26. So we're going to get pretty close to the same thing right here, because that's 419, that's 418. But let's just get the number down. Why not? So we get we're off by 2.85% less. Interesting. It's probably better to use the compressed water tables, but this in a pinch might be a viable option.